All right. Good morning, good afternoon, good evening, everyone. Thanks for joining today. We will get going now that it's 10 a.m. And so today I'm really excited to have Michael Fromberger with the language analysis lead for Sourced, recently hired from Google. Michael will talk about the Kythe open source project. So please take it away, Michael.
Thank you, Victor. Hello, everyone. Thanks for joining us today. The title of my talk here is The Road to Semantic Indexing. And I'll talk a little bit more about what that means specifically, but just as a note, the slides for this talk will be available afterwards. They're not currently accessible, but the link is on there on the first slide, and I'll make sure that when we're done, I actually make them readable. So, as an agenda for the talk today, this is basically intended to be kind of a high-level introduction to the Kythe project, what Kythe actually is, from a developer's perspective, but not with a lot of implementation details. And so, although this isn't primarily a technical talk, I will cover some of the details of how Kythe works in sort of a high level, so you can get an understanding of how it accomplishes what it's intended to do and how it can be applied to solve certain problems. I would actually love to talk more about some of the implementation details, but that could easily run to 2 or 3 hours. It's a talk that I used to give to new people joining the team, the Kythe team at Google, about when someone would join, how it all works, and it would fill up an entire half day afternoon of meetings. So we'll have to split that into smaller pieces. And so for now, we'll focus on what we can fit in a more reasonable time. Also, it's probably worth noting there will be some links in this slide deck, or these things referenced by links, and there's a slide at the end that has all the actual URLs on them. So again, don't worry about being able to get them. You will be able to get the links from the end of this slide deck when we're done. So that's the introduction, and the rest of the agenda basically consists of what you see here. We'll talk a little bit about the history of the Kythe project, what it is, and at a very sort of top-level view, and then we'll dig into a little bit to how it works, some of the goals and assumptions, and then actually go over some of the Kythe schema, which is in some sense the primary component of Kythe as a project. And then we'll leave some time, hopefully at the end, to wrap up. And if you have any questions, you can add them here in the presentation. There's a Q&A tool, or you can chat to Victor and let him know you have questions, and he will make sure that I get them and hear them. Yeah, so without further ado, as I said, we already introduced me. That's who I am. I am currently just recently hired at Sourced, so I'm still learning my way around. But the high-level thing that I would like to try and accomplish, and this is something that I've been working on for a long time now, is to try and help to reduce the fear and friction associated with making changes in source code. Right now, a lot of people, when they develop source code kind of in isolation. We vendor all of our dependencies, and we sort of don't do updates very often because the cost of doing that is actually very expensive. What's going to break us this time? And part of the challenge, of course, is that we depend on so much stuff, and so much stuff depends on our code, that it's hard for us to see what will be affected if we make changes. So part of the goal of projects like Kythe is to make that more visible to us, to make it possible for us to tell what the effects of our changes will be, and therefore to make them with less concern about the aggregate effect. So Kythe, what is Kythe? The name Kythe is actually, rhymes with scythe if you like. It derives from an old Germanic word, Kythe, which meant to make known or to reveal or to tell. It's actually based on an internal project at Google called Grok that Steve Yegge founded back in 2008. Grok, obviously the word from Robert Heinlein's novel, Stranger in a Strange Land, meaning to deeply understand something. Unfortunately, we couldn't use the word Grok for a public project because the name was already used in lots and lots of other places. So Kythe was a word that we found that was easy to search and means kind of the same thing. Although I won't deny that it's a little bit weird to pronounce the first time. So Grok was founded in 2008 as an internal indexing project. The goal was to basically generate what we now think of as a semantic index for all of Google's code. And it turns out, despite people's skepticism about that it worked pretty well. So in 2013, I and the other members of the Grok team wrote a proposal to release Grok as open source. And then in 2015, we actually launched the first beginnings of the project on GitHub. And so there's a link to the Kythe project, which is sponsored by Google, but it is an open source project. And in fact, actually, the open source project, all the code that's there is what Google uses internally for its index now. That was one of the accomplishments that we were able to achieve. So, there we go. So, what is Kythe all about? I mean, the fundamental question that we're trying to answer is, someone comes and says, hey, I want to be able to do this with source code, right? Syntactic things like selecting pieces of the code that have certain properties, or simple linting and formatting tools like, to sort of manipulate your code as a blob of text. But there are also a lot of semantic queries that we'd like to be able to answer, right? And we'd like to be able to have cross-references. We'd like to be able to have symbol lookups and call graphs and visualizations and type structure and all these other things about our code. And of course, once you have those capabilities, you'd like to be able to build on top of them to be able to do refactorings and dependency analysis and more sophisticated static analysis problems. And the natural thing that you'd say when you consider this is, well, I mean, my IDE can do that, right? And it is true that it can, but for only a subset of the tools that you care about, because each IDE has its own strengths and weaknesses, some things it supports and others it doesn't. For only some subset of the languages that I use, since each IDE typically works really well for some languages and maybe not so well for others. And for the subset of my code and its dependencies that I can kind of fit locally on my box. I think anyone who has used Eclipse or IntelliJ has experienced the pain of waiting for reindexing to happen when the project gets really big, its dependency footprint gets large. And then also, of course, for the subset of the developers who actually use that particular IDE. And no two developers completely agree on what the development environment should look like. And so part of the challenge here is that we'd like to be able to solve these problems without forcing everybody to adopt one true way of solving their problems. People should be able to use the tools they're comfortable with, whether that's Vim or Emacs or IntelliJ or Eclipse or Sublime Text or whatever it is that people like to use. And that in some sense, the solutions to these problems shouldn't have to depend deeply on being in a particularly canned environment. So that was the motivating idea. And so when you look at a lot of tools that solve the I want to do X with source code problem, they have a kind of a common structure, right? They have to find the source code they want to work on. They have to lex it and parse it. They have to resolve dependencies and types and symbol names, build up an AST in memory and, have type information and know what the dependencies are and all these other things. And so if you look at that, I mean, really what you've got at that point is the front end of a compiler. I mean, that's basically what a compiler does. And in fact, some programming languages don't actually have a compiler per se, but essentially, if you want to be able to do those kinds of tasks, you have to implement that kind of thing. But unfortunately, because as it turns out, these things are often hard to do, particularly for some languages, we often end up re-implementing these by hand for each new tool or each new language. And often we end up taking shortcuts because it turns out that it doesn't exactly work the way it's supposed to. So we use globs and regular expressions and shortcuts in order to solve a particular problem. And the result of that means that we wind up reinventing a lot of wheels as we implement these tools, and each one reinvents them a little tiny bit differently. When in point of fact, what we're really doing is reinventing part of the front end of a compiler or simulating parts of the front end of a compiler. And so the insight for Kythe was that, this is a real pain. This means that not only do you have to build this for your tool, but you have to do it M times, one for each of the M tools that you want to support, and each for N languages that your project supports. And so that means that essentially you have this kind of, cross product that you have to solve in order to have all of your tools work on equal footing with all of your languages. And even a small project has multiple languages in it. We tend to think, my app is, it's a Rails app, so it's all in Ruby. But, your deployment scripts, there's some Python, there's some Bash, there's, maybe some JavaScript in the front end. So every project, even a tiny one, has actually a fairly surprising footprint in multiple languages. And the dependencies between those are actually really interesting. They're what makes building and testing and deploying and so on difficult. So the goal with Kythe, at least at an abstract level, is to convert this M cross N tooling problem into an M plus N integration problem. We'd like to say, well, let's have, at least for certain problems, a shared language that we can use to communicate semantic information about each language to the tools that care about it. And then the problem becomes then not just to integrate each pair of tool and language, but each language and then each tool separately into a shared schema. So Kythe's approach is basically that. We have a language agnostic graph language that is intended to be extensible so you can add new kinds of data to it, and that you can plug in languages into it independent of what UI they're intended to communicate with or what static analysis tool they're intended to communicate with. And that you can then, based on that, define APIs that express interesting queries that users have, like where are all the places where this function is called, or simple things like that, or more complicated things like where are all of the expressions that have a type whose type parameter is an instantiation of some subclass of this class, right? Those are sort of really interesting questions that we'd like to be able to answer when asking what will be affected when I make changes to my code. And it's simple enough to state, but I think it's worth sort of looking at this a little bit more closely, is that the goal of separating these things out into a sort of a communications language is that it allows you to disassociate the query from the implementation details, which is difficult to do when you're working in an integrated environment, which sort of has all of its assumptions baked in. And one of our key principles in design of Kythe is that the query should drive the rest of the system, meaning that if you know what query you want, right, where is this function used, and you know some constraints on like how you want to use it, like I'd like to be able to get, my responses for this in under 50 milliseconds at 95th percentile, then that gives you an axis against which you can cost the rest of the technical decisions that you have to make in implementing the rest of the system. So in addition to being a sort of high-level complexity solution or attempt to solve that high-level complexity problems, it's also an attempt to drive the solutions of other technical challenges from the customer's end of the equation, which is often, as anybody who works on developer infrastructure or really infrastructure in general can tell you, is actually really often hard to do because your customers are often insulated from you. So we have several assumptions that we've made in the design of Kythe. And there are lots of ways we could go into this in lots of detail, but I just want to talk about a few of the high-level ones. Assumption number one is that completeness matters. That is to say, we really want to index all of the code that you depend on, not just the source files that are in your repo, but all the tools that you depend on and all the libraries that you depend on and the libraries and tools that they depend on, so that when you ask a query like, where is my function used, you really can get a comprehensive answer. And that means, therefore, that we care both about your forward dependencies, meaning kind of the active order dependencies from your project on other things, but also the reverse dependencies, the passive order dependencies of other projects on you, because of course that is also affected when you make changes to your own code. And an observation that we've generally made is that completeness therefore means that we have a problem of scale, since even a very small project has a very large dependency footprint. And the ability to scale static analysis is generally limited by the degree to which it can be parallelized. And our general experience has been that analyses that work forward in the dependency graph can be scaled pretty well, and that analyses that work in the reverse of the dependency graph generally can't. So this distinction between forward and reverse turns out to be kind of useful as a tool for understanding the complexity of a dependency graph. Another assumption that we make rather is that accuracy matters. And that is to say, we really want the results that we have in our index to be correct. We don't want them to be sort of approximations of truth, but we would like them as much as possible to correspond with what really happens. So where practical, for example, that means we want to use a real compiler for the programming languages that we index. This is important, I think, because of course, you can sometimes approximate solutions to queries, but anytime your tool differs from what actually happens in production, it's giving you false predictions, either false positives or false negatives, depending on what you're looking for. And those are expensive because, of course, you would like to have trust that your tools reflect as closely as possible what is statically true about your code. Another thing that we think is important is what I like to call isolation. That is to say, we think it's important to encapsulate language-specific details, not spread them across the entire system, to say that like each component has to know about this particular language's foibles and throughout, but to say that the knowledge that we have to have about, say, C++ or Java or Python or whatever it happens to be, should be the responsibility of a single component responsible for doing analysis in that language. And then finally, it has been our general observation that there is a great opportunity for what I like to call leverage here, which is to say that a lot of the things that we've talked about doing, indexing source code, indexing semantic information, actually turn out to be really expensive to do at a large scale. And therefore, whenever possible, we'd like to reuse the infrastructure for doing that to solve other kinds of problems. In a lot of ways, we'll talk more about the details in a little bit, but in a lot of ways, you can think about Kythe as a semantic index as a kind of a minimum viable product for static analysis tools more generally. It's the simplest possible thing you can do that doesn't require, that requires sort of at least as much effort as compiling your code does. But once you have that, it turns out you can build lots of other really interesting things too. And in fact, also at Google, there is a project called Tricorder, which is essentially about taking the infrastructure that we built for Kythe, for Grok originally, and then for Kythe, and then using it to apply other static analysis tools to the same code. And this allows large-scale refactorings to be done. This allows all kinds of really interesting higher-level tools to be built on kind of the substrate that we needed in order to do this sort of basic indexing thing. So finding opportunities for that kind of leverage is really valuable. And so in our design of Kythe, we tried to keep these 4 things, among others, in mind. So that's like a very high level view of what Kythe is. It's sort of why we created it. And now I would like to take some time to dig a little bit more into what Kythe actually looks like. That is to say, we talked about Kythe as being this kind of schema for communication between language tools and UI tools, and that's a very vague sort of statement. So I'd like to actually make that a little bit more specific. So basically, if you look at it at a low level, Kythe is essentially a set of rules defining a graph structure that represents semantic information between program structures, source code program structures. And like any kind of a textual index, and when I say index, I mean this in the usual sense, right? That an index mapping from documents to terms. But in a semantic index, the documents in this case are files or programs, and the terms are not necessarily just lexical structures like sort of identifiers or words, but also program structures like functions and variables and types and classes and various other things that you define in your program structure and the relationships between them. So, at a very high level, the Kythe schema consists of, as I said, it's a graph. And as a graph, it has nodes and edges. And so those are the sort of fundamental building blocks of what Kythe actually is. A node, from Kythe's perspective, represents a semantic object of some kind, like I said, a variable, a function, or a type. And nodes are identified by these strings called tickets. I'll talk a little bit more about a ticket in a minute, but broadly speaking, a ticket is essentially a unique ID for a node. It's essentially something you need in any graph structure. You need to be able to way to name things. And in this case, the real challenge of pretty much all of Kythe is actually how to assign these names in some useful way, how to discover what they are, and how to ensure that that a particular node you discover in one part of the graph is the same as the one you discover somewhere else. And then, in addition, each node has associated with it some key value pairs that we call facts. The actual facts and their names and their values are defined by the schema doc, which is linked on the below. It's just a reference guide to all the things that we've thought of that make sense so far. But broadly speaking, it's a name, like Kythe node kind, and a string value. And so this, for example, fact, this Kythe node kind fact defined by the schema gives a category to nodes that sort of talks about, not in the mathematical sense, but in a sense of grouping of nodes into related kinds. And of course, we also have edges, and as in any graph, these denote relationships between pairs of nodes. And basically, if you can think about an edge as just a pair of tickets with a label saying what the relationship is. So for example, the example given on the slide here is called Kythe edge extends, and that basically represents a relationship between one type that is an extension, subtype of another. One of the interesting things you find when you start looking at these concepts is that despite the fact that each language uses the same terms, or many languages use the same terms, like class and so on, that they don't mean exactly the same thing from one language to another. So for example, the semantics of class in Java, and the semantics of class in Python, and the semantics of class in Ruby, and the semantics of class in C++ aren't exactly the same. But, a reasonable programmer can kind of squint and pretend that they're basically the same thing. For the purposes that we care about, they're essentially user-defined types with some field structure and some methods attached to them. And that's actually a useful generalization of class, even though it's not mathematically precise enough to necessarily predict things about a specific program. So we have nodes and edges. And I mentioned a minute ago that we have nodes identified by these strings called tickets. It turns out that the naming problem is actually the hard one. And so what a ticket actually is the string encoding of a more elaborate structure that we call a vname. Vname is not an existing term. It's something we made up because we wanted to have a way to describe the idea that we have nodes and they have names, but their names are not the same as, for example, the name of a variable in a program, or the qualified name of a class in JVM. So the conceit that we have for naming nodes is to basically, you can imagine that a node essentially consists of all of the attributes that a particular program structure has, right? It has names, and it belongs to a particular repository, and it lives in a particular file, and it has, this particular type signature associated with it by the compiler, and various other things. And so if you think about it from that perspective, a node in a program is really just a big vector of attributes that node has, and that each node is essentially that collection. And so the abstract idea behind a vname is that we want to be able to find a projection of that vector a small projection of that vector that has enough attributes in it to uniquely identify that node without having to know all of the rest of them all at one place. And then we can use that to uniquely identify the node. And that basic idea is the motivation behind how we name nodes in Kythe. So we picked a set of attributes that we thought were sufficient to identify a node in Kythe, and that includes this list of 5 attributes listed on the slide here: corpus, language, path, signature, and root. And basically, the idea is that corpus describes what body of code the node belongs to. So for example, typically this would be a repository. The language, obviously, defines what language owns the node. Is it C++? Is it Java? Path is included, for example, if you have things that have a path structure like package names or files. Signature is the compiler's own sense of the identity of that object, sort of an opaque blob that the compiler knows the name of, whatever it happens to be. The sort of the contents of that are not defined. And then root is essentially an extra degree of freedom that we found was useful for dealing with things like generated code, where you have a repository and you have a code generator that kind of injects some additional generated code over the directory structure, but it's sort of an overlay on top of it. So basically just a way of saying this can, the root can express things like generated code or branches or things like that that are essentially overlays on the same directory structure. But our goal, sort of 2 things about this that I thought were worth pointing out, is that we wanted as few degrees of freedom as possible to be able to describe everything. And so far this has worked out. It is extensible if need be. The vname is extensible. But we wanted to try and keep it small because names are going to be mentioned everywhere. And the other thing that's important about this is we don't include in the name of things any sense of time or version. And it's something you could argue maybe you should. We actually talked about this quite a bit. But the conclusion we came to was that basically the vname of an object should not vary over time unless the meaning of the object also varies over time. So versions and timestamps and things like that correlate with the meaning of things changing, like semantic differences, but they don't cause semantic change necessarily. So we actually consider version and timestamp and things like that to be separate concerns. They're more the property of a whole graph, right? This is the graph that existed at a particular timestamp or a commit position, rather than this entity had this particular identity at that commit position. Because we would like to be able to tell when a particular class remains the same from one commit to another. And that's actually an interesting piece of information. So we have nodes and edges, and nodes are identified by these tickets. Tickets are essentially just a string encoding of these vnames. And now you basically have the core of what Kythe consists of. Those are all of the concepts that Kythe includes. And the rest of the schema basically consists of rules for how to combine them. There's one more thing I want to talk about a little bit before we go on into some of the specific details of the schema. One of the things that you find you need when you're trying to do semantic indexing, right? I'd like to be able to know that this function calls that function, for example, is you have to have some way of talking about where something is defined or where a call occurs or whatever it is that it happens that you want to represent. So you need some way to represent location. So there are a couple of designated things in Kythe specifically to deal with this. One is there are nodes representing files. As you would expect, there's a node that describes a particular file. And then there are nodes called anchors that represent a particular span of text within a file. These are special in the sense that anchors are the one kind of node that is sort of not really truly semantic, in the sense that this designates a physical location rather than a semantic object in a source file. But having these allows us to capture the amount of information we need to do basic indexing. A couple of important points about that, though, is that Kythe doesn't capture the complete syntax of the file. It could, and we've actually done some experiments with that in the past. But it's very expensive to do, and we didn't really need to do all of it in order to solve some of the interesting problems, so we didn't. But Sourced actually has a project called Babelfish, which actually produces a more generic so-called universal AST structure, a language-agnostic AST structure that does in fact actually capture the complete syntax. And one of the things that we're looking at doing in the future, or that I'm particularly interested in trying to do, is to merge the semantic information we get from Kythe with the universal language agnostic ASTs from Babelfish to allow us to answer more sophisticated queries. So this is definitely a possible thing. The design choice we made for Kythe was to choose only a very minimal set of location information, but it is of course possible to do more. And I hope that we can combine them. So now let's actually look at, we have nodes and edges, and we have anchors and so on. Now let's actually look at what Kythe defines as some of the interesting schema fragments. In other words, the pieces of the graph that represent certain interesting program structures. So in the slides that follow this, there are going to be some diagrams, and these diagrams will follow the key that's actually represented on this slide here, that a box, a rectangular box, is a semantic node, that is to say anything but an anchor. A round oval box is an anchor representing a location in a file somewhere. And then the edges with their labels describe the relationships between them. These are very high-level schematic details. If you actually look at the results that a Kythe indexer produces, there's actually a lot more sort of intricate. There's facts that each semantic node has attached to it, and so on. And I haven't drawn those in these diagrams just so that we can kind of see what the relationships are. But there's more detail. There's actually, the Kythe project has a schema overview doc that we generated. And you can actually go, the examples that I'm about to show you are more or less derived from those. So the interesting thing here is that if you look at it, a graph, right, because it's an arbitrary structure, it has arbitrary complexity, but inside of it, there are a lot of interesting subgraphs of useful information. And so part of the way we've defined the schema is by identifying some of those subgraphs as particularly useful for answering certain questions. So the first one we'll look at is, I think, probably the most obvious semantic query you can think of, sort of the jump to definition query, meaning I have a thing, a variable, say, or a function, and I'd like to find out where it's defined. So the way that this is represented in Kythe, you notice there's a code sample here, sort of a trivial code sample with a variable declaration for a variable x of type int, and then a little further on, a return statement that has a reference to x, actually two references to x. And so the question is, how do we represent the relationship between those uses of x and the definition? So in Kythe terms, this is pretty straightforward. We have an anchor for each of the locations where x is used. Sorry, I think that it looks like the subscripts didn't work out exactly as I had hoped, but notice that the subscripts in the text in the example code don't, obviously, they're not part of the real source. They're just indexes that I stuck in so you could tell which x I was talking about. So x1, x2, and x3 are anchors, representing the places in the code where x is mentioned. And then there is a semantic node representing the variable x. And there are sort of two interesting relationships here. One is called the defines binding relationship, which says that x1 defines a binding for this semantic node for the variable x. So that allows us to discover where the definition actually is for x. And below, x2 and x3 have ref edges, which mean that these are references to this semantic node, this variable x. So now if someone wants to jump to definitions, say you're implementing a source browser or something like that, right? You can say, well, okay, at the location of x2 and x3, I have ref edges that point back to this semantic node x. Great. Now, from that semantic node x, where is it defined? And that takes you back through the defines binding edge in reverse to x1, and that tells you where the definition is. And again, I mean, this is not super complicated. This is not intended to be complicated. This is just the simplest possible representation of a fairly generic relationship that exists in most programming languages between uses of a named object and definitions of it. The important piece here is that the semantic node actually has its own identity, and that you can in fact have a variable that it could be in general defined in multiple places or declared in multiple places. Consider, for example, the C family of languages where you can forward declare a variable and you can define it in, well, ideally only one place, but those all should be related to each other, and this mechanism allows that to happen. So that's the simplest fragment. Another fragment of interest, a little bit more complex, is a call graph. And so a call graph is an interesting structure because it's actually three-sided. You think of a call graph doesn't really just go from one object to another, but there's sort of three components to a call. Traditionally, in a call graph, you would have a triple, where there's the caller, the function that actually contains the call site, the actual location and where the call happens, and then the callee, the target of the call. So those three are all actually interesting for the purposes of knowing this. So we have here a code sample again with two function definitions in Go, f and g. F calls g, and then down below there's an assignment of a throwaway variable to an invocation of f. So there's a bunch of things going on here, but broadly speaking, it's just a generalization of what we talked about a minute ago. We have anchors to represent the locations of f. F1 is the location where f is defined. F2 is a location where f is called. And so you see this function f semantic node, the rectangular node, it's defined at f1 and called at f2. Okay. And then function g also has a semantic node defined at g2 and called at g1. And so that's two parts, 2/3 of the call graph, right? We have the location where the call happened, and we have the function that was actually called at that location. The other piece that we need is to know the association between the caller and the callee. And in Kythe, this is represented by an edge we call child of, which basically says, and so in the case of looking at G1, for example, the anchor G1 is marked as a child of function f. And that means that the call site at G1, which is a ref call to function G, is located inside the body of function f. So now we have the relationships that we need. You could, of course, have done this in a different way. This just happens to be one way you could represent this, but you can now recover the entire triple from the graph structure that you have. And this particular choice of which nodes and edges to, or which edges to point, was mostly made based on the difficulty of generating them in the analysis process. There's one more child of relationship here that I glossed over. Somewhere there is a function, with the way I wrote the source code, there's a package level init function that evaluates all of the initial assignments at the top level of a package in Go, the package init function. And so the call to f that occurs at f2 is a child of that init function, since that's the calling function for f. So here we have, again, a fairly simple structure, but this, again, follows the same basic principles, and you can think of this as a unit. If you want to implement call graphs, these are the nodes and edges, the kinds of nodes and edges you would need to emit for your particular language. Another interesting graph fragment that we might care about is membership in a type. So a lot of languages have structure types of various kinds, classes or structs or records or whatever you want to call them. We call them records in Kythe. But the basic idea is anything like a struct in Go that has a name and some fields in it, or a class in Java, and perhaps some methods attached to it. So again, the code sample in Go here defines a type T with one field and one method F. And so again, you'll see that the graph structure here is not all that dissimilar. We have a record node for T, a variable node for its field N, and a function node for the method F. T1 is the definition site for the record. N is the definition site for the field, and F is the definition site for the function. And then the other relationships that we have here are that function F is a child of the record T, which indicates this nesting relationship as before. This means that function F is semantically associated with the type. And that's how we indicate method membership. And then similarly, the variable N is a child of the record, meaning that that field, that variable, is a child of that type. And then at T2, we see that there's a reference to the record type. It's just basically to indicate that this particular graph fragment talking about class membership or type membership can nest together or can join together with fragments from other widgets in the graph, and they all work together in sort of the normal way. So again, a fairly simple structure, but again, it sort of allows us to answer simple questions like, what are all the members of this type? What functions does this type expose? That kind of thing. And you can then, of course, say, well, where are all the places where someone uses a field that is a member of a type that has this property, right? So you'd be able to have this somewhat structural relationship at the semantic level, not just at the physical level. I chose Go for this example partly because most of my examples are in Go, but also because it points out the fact that semantic structure doesn't necessarily follow lexical structure. So in Java, the methods of a class are defined inside the class definition, but in Go, they're not. They're out of line. In C++, it's a little bit of both. You have to declare them inside, but you may define them offline. The model wants to be able to hold both of those without having to kind of do something really unnatural. So instead of following the lexical structure directly, we have this semantic relationship child of that indicates a kind of a nesting. Another interesting fragment is type hierarchy. So here again, I'm using Java in this case. It's a little bit easier to see, although you can actually express this same relationship in Go. We have a class C and a class D that extends C. And so again, to represent that, we have some anchors. C1 and D are definitions for classes C and D respectively. Note that in Kythe, even though Java uses the keyword class for these, we call them records. Again, this is sort of part of the semantic model where we are simplifying, we are squinting and saying all of these things that have this record structure are kind of similar enough that we are willing to consider them similar. And then C2 is a reference to class C in the definition of D. And then the important piece here is that record D extends record C. That's how we capture the relationship that one is an extension of the other. Again, nothing super complicated, just an application of the same principles as before. The interesting point about this example, though, is that it then allows us to express other interesting relationships, like in this case, overrides. So here we have the same example as before, except now I've added two methods, a method F to class C, and then an override for F, and an override for F to class D. So the grayed out part is just the stuff that was there from the previous slide, right? The record C and D with the extension relationship. But now we have two additional function nodes, one representing the method of F on C and one representing the method of F on D. Each of those has its own definition site as before. But now, and also as before, C is a child of, C : F is a child of C, meaning it's a member of that type, and similarly DF of D. But now we have this additional overrides edge that captures the fact that when the D is overriding specifically that particular method of C. And this seems pretty trivial, and again, the model is not complicated, but the interesting point about this is that now we have this relationship, we can answer interesting queries like, well, it turns out if I have a variable of type C and I call a method F on it, at runtime I could be calling it CF or I could be calling DF or potentially other things, right? Because the override relationship allows me, the dynamic dispatch allows me to call any subclass member with the correct signature. So now I have a way to express in this very language agnostic way the idea that I can detect which classes are statically known to have the correct type to dispatch safely at that location. So in addition to just the subclassing relationship, we can also express overrides. And as before, there are binding sites for those so that we can do jump to definition. So all of these things connect together into one coherent model. I'm pointing them out as sort of isolated examples, but of course in practice, when you index, you have all of these lumped together into one big graph. And moreover, once you have these relationships, these sort of one-hop relationships, you could actually do them, explore them transitively. You can say, well, you know, where do I have a set of overrides that may have multiple options in the chain between the class that I actually have and the one that I actually call at runtime. Another interesting case are functions and parameters. And again, here, nothing too surprising will be here. We have a function definition in Go, f with 2 parameters, x and y. And as before, we have a semantic node to represent each of f and of x and y, a function and 2 variables with binding definitions. The only new piece here is that we now also have these edges called param0 and param1, actually param-n in general, which capture the relationship between f and its parameters. So now this gives us a way to be able to say, hey, I have a callable thing, a function or a method or maybe something with an overloaded call operator. How do I find what the parameters are for that object? You can follow now the param X edges to be able to discover what those are. And that allows you to answer interesting queries like, where do I have a function whose first parameter has this particular type, and that kind of thing. So again, this sort of it gives you a semantic structure of a callable function. There are several other things in the graph schema that are similar to this in structure, but I'm just showing functions and parameters as they're kind of the simplest ones. And then last, but probably not least, the other thing that this allows you to do is to capture documentation. And you might argue that this is sort of not really a semantic thing, but as it turns out, there's kind of a weird hybrid view about documentation. Is that in some senses, it's a textual thing, right? You write some comments in your code. But in other cases, it has a semantic role in the sense that the particular documentation is associated with a particular semantic object according to certain rules. Sometimes those rules are simply lexical, like Java comments are required to immediately precede their object and to have a special comment notation, as I've done in the example here. In other cases, they're actually baked into the AST, as in Go. But in general, so the compiler often has knowledge of these associations. And in particular, it's also possible for documentation, as in the example that I've shown here, to have links to other interesting semantic values inside of it. So in this Java doc here, we have a class Z, and it has a link in its Java doc pointing to some other class that we would like to be able to record the fact that, you know, that relationship was known. So there are actually a couple different ways you can represent this in Kythe, but probably the simplest to understand in this case is that there is a node kind called doc, which represents a document of some kind. That doc has a fact, a text fact that I've illustrated here with the sort of light blue node that extracts the text without all of its comment markers and all of the other stuff attached to it. And in addition, that text can have markers in it saying, here is a particular region of text that the, say, Java doc parser identified as being a reference to some other object in the graph. And then we reuse the parameter relationship for doc nodes, just like we did for function nodes, to capture the idea that these are in some sense parameters of the documentation. So we then have an edge pointing to the node for the record type A, probably defined somewhere else. We don't have the definition for it here in the example, so I've only shown the node grayed out. But in general, you'd have somewhere that is index that node, and you can now point to it. And this allows you to do all kinds of really interesting things, sort of not purely semantic, but semantically related. Like you could have a UI that displays hover cards, and the hover cards contain links to things, and you can get cross-references for them. And you can also find where there are references to something in documentation that mention your code, so you know which documentation you need to update without having to go through extra steps. So. The high-level point I wanted to sort of make here is that there are various pieces of this graph structure that you can extend to handle various interesting queries you want to be able to answer. And these are a handful of the ones that we found interesting to answer within the Kythe project for the cross-references that we needed to provide. You can sort of course, define your own for new kinds of structures with varying degrees of difficulty. And once they are defined and become part of the schema, you can teach analyzers to emit the data that they need in order to be able to actually get these structures included in the graph. And then it means that someone who wants to consume Kythe data, a UI tool or a command line tool or whatever, does not need to understand the particular language, but only the schema rules surrounding that particular feature, say documentation or functions or whatever, and it can operate on them in a language agnostic way. So, just to summarize what we did a minute ago, just sort of went over a handful of the Kythe schema's sort of graph fragments, if you like, subgraphs, each of which defines a particularly interesting feature. And the important thing about this, as I just said, is that the indexer that we talked a little bit before about isolation of responsibility. When you want to make an indexer for a particular language, you then don't have to worry about lots of operational details like how it is that you actually discover where the source code is. You simply say, hey, given the source code that I have to index, what are the facts and the nodes and edges and so on that I need to emit in order to represent this particular feature that I think is important to my language? So as the author of an indexer or of an analysis tool, you have control over how to represent these concepts in your language in a particular language agnostic way. There's tons more detail about this in the schema reference doc, which we have linked at the end. I won't go into it in great detail at the moment, just to say that this is sort of a very high level view, and we're only really talking about parts of it right now. So with that, I have covered all of the pieces of the Kythe schema that I have listed, and I would like to know if anyone has questions. I saw some flashing earlier, which suggests there might be.
So Mars asked a question. She says, what kind of contribution to Kythe project are most welcome at this stage of the project?
So the thing about Kythe that's challenging is that the thing that makes Kythe difficult to do is sort of two pieces, really. One is how to integrate with the build system sufficiently that you can get a hermetic record of source code in sufficient detail to index it. So there's sort of one point of contribution that's very valuable is tools that can integrate with particular build systems. So for example, for historical reasons, the Kythe project uses the Bazel build system, and so it has very good integration with the Bazel build system. This is not surprising given that it came out of Google. But other build systems are not very well supported. So the Kythe team, for example, is working on Maven right now, and I think also Gradle and possibly CMake. But any other build tools like that that can capture buildable records of source code, like say this is a package or a module or a whatever unit of buildable source, and making those exposed to the rest of the system is really valuable. I didn't really talk in operational detail about that level too much, but that's actually one piece. The other is, of course, language analyzers. So if you have a favorite language that isn't currently supported by Kythe, another thing that can be really helpful is to work on an analyzer for that language. So there's a laundry list of languages currently supported. C++ is supported very well. Java and Go are both supported very well. Someone at Google is working on a Python integration. I don't know the current status of it anymore, but it seemed like it was in pretty good shape when I left a couple months ago. But there are a lot of other languages that people care about that aren't necessarily covered. So again, if you have a particular interest in a language, I know there's some Scala fanatics out there, maybe Clojure, that's actually a sort of fairly self-contained way in which people can contribute.
Another question from ISO. Has anyone integrated LSP with Kythe?
Yes, actually, the Kythe project actually has an LSP service, sort of. It's not a great integration, but not a very powerful one. But basically, the idea is that it runs a little LSP daemon on your local box, and it pretends to be the workspace, and then it can call out to a Kythe index of the code that you have. This, of course, requires that the index exist, which is the limiting reagent on most cases right now. But yeah, there is an LSP sort of plugin, if you like, or server in the Kythe repo. It was written by an intern that we had a couple of years ago who did a really nice job on the LSP integration. But the thing that's missing right now is that it's actually still kind of hard to index globally.
And Xavier is asking, is it in the roadmap to analyze project that depends on REST API?
So yes and no. Yeah, so the problem with REST APIs is they typically don't have a schema written down. I mean, they have a schema, like sort of defined in code. So broadly speaking, at Google, we use, rather than REST, we typically use protocol buffers and RPCs, basically the ancestor of gRPC. And there we actually have an indexer that I think someone's working on open sourcing right now that can consume the protocol buffer definition files and produce an index. And we actually have a mechanism in the schema for being able to map between the generated code for the proto definitions and the actual schema source. And that would actually allow you to bridge back and forth between the definition of the API and the actual implementations and usages of the API. But that isn't generally available outside Google yet. A, because the proto indexer is still not been exported. I think they're working on that right now. And then B, because REST APIs typically don't have a schema like that, although I realize there's some conventions that people have used. It is, however, possible. And so in general, if we could use that to encourage people to write down their APIs in a machine readable form, I think that would be fantastic.
Is Kythe a code search tool, a code analysis tool, or both?
It is really not a code search tool at all. It's really very much it's kind of a framework for hooking code analysis tools to code. The Kythe schema specifically addresses certain very specific use cases. So I talked a little bit more earlier about sort of the minimum viable product nature of Kythe. That cross-reference sort of thing, the schema fragments that I showed in the slides are kind of an example of that. But realistically, you could hook other analyses to it. There are analyses that would be still hard to do even in this framework, but for a lot of analysis tools that you could basically reuse the same infrastructure. So for example, internally at Google, they reuse a lot of the same infrastructure for doing static analysis like error-prone, the error-prone tool for finding bugs and other things like that, that even though they are in fact actually language specific, they can reuse the same infrastructure that we use to build and capture and analyze, and then to emit their results in a language agnostic way that can be surfaced for code review. So yeah, I mean, the potential is there, but I don't want to oversell the current state of things. There's a lot of work to be done to actually make that practical right now. And a lot of it really boils down to the fact that build environments are still very much not hermetic, generally speaking, and tool chain dependencies aren't often well characterized and so on. So we have a lot of work to do, but yeah, it should be possible.
And the second part of the question is, could you give an example of where Kythe shines compared to other search/analysis tools?
So the biggest thing that Kythe really supports that I think it's hard to really see right now, although I can try and show you a little bit of an example, is in being able to index not just your own local code, because as I said earlier, like your IDE can index your local code just fine, and it can do it faster than Kythe often can. But in being able to index the complete set of code that you depend on, in other words, to have a global scale index that can actually answer your questions, not just about your own code, but about the code that depends on your code. And that power is not currently generally available. And that large scale, or the capacity for large scale, is actually, I think, the real advantage that Kythe has over other things. I mean, I really see them as complementary rather than sort of conflicting. You typically would want to still have tools like local IDEs and things like that to analyze recently changed code or code you haven't submitted yet or things like that for your own purposes. But for larger scale questions like what will break when I release this API to the world, you really want that large scale. So, but the reality is there's a lot of work to do to get from here to there. And so one of the things I'm hoping to push on as I get more comfortable at Sourced is to start taking some of the sort of large scale infrastructure that they've already built for doing analyzing Git repos and to start kind of push some Kythe indexing into that. We'll see how well it works.
Another question, what happens if you don't know much / anything about external functions, classes, etc. that you might be using? And do the calls still get indexed in some way just without the definitions?
So there's sort of two parts to that. One is that if you don't know what they are at all, then you probably won't be able to index the association. So the real key to Kythe indexing is that you have to be able, your indexer has to be able to utter the ticket for the node that it refers to. So if your indexer can do that, even though you don't have the code locally, that's actually fine. So for example, if you've downloaded a jar file from Maven, you don't really know where the source code is, but you have the class files, then yeah, you can absolutely index that code. You can record the fact that that function call happened. And in fact, actually, that's the intended use, right? That you don't index everything you depend on all at once. You index your piece and they index their piece and then everybody else does theirs. And then we combine them all together into one graph. But on the flip side, if nobody indexes that, or if it's not known to a sufficient degree of precision that you can actually spell the ticket for something, then there really isn't any practical way to do it. So yeah, I mean, that actually, depending on which direction you meant, that is either the intended use or an unsolved problem.
And one last question. So would similar to gRPC approach work for JNI and other native bindings?
Yes, in fact, we actually had a prototype a few years ago that did JNI specifically. I also think CGO might be possible, although we haven't tried it. Basically, what you need to do in order to make it work is you need to be able to instrument the code generator or something that can pretend to be the code generator. So what we do in for protocol buffers, and the same approach works in general, is that, so the challenge is, right, that how do you know what the name of this object that you're generating the code for will be in that language? A code generator is typically just a Perl program or a Python program or something that spits out text. It doesn't know anything about the syntax or semantics of the language in any meaningful way. The author knows, but that information is not recorded. So instrumenting the code generator to emit additional metadata, perhaps under a flag, so when you're indexing, you can do that, allows us to capture the relationships between the generated code and the schema. And the same thing can definitely work for, I know it works for JNI. It could potentially work for most other FFI type bridges built based on code generation.
Well, I think that's, we're a bit over time now, and I think that answers most of the questions. Thanks so much, Michael. That was great. And everyone, thanks for joining. If you have any topics that you'd like us to cover, feel free to shoot me an email at victor@source.tech. Or join the meetup page to get informed of the upcoming meetups. Thanks, everyone. Have a good day.
Thank you, everyone.